In this video, we're going to look at the volumes of the solids that we obtain if we rotate a curve by 360 degrees completely around either the x-axis or the y-axis. So, let's start off with a possible curve. So we're going to look at the curve which consists of y equals 1 plus 0.1 times x squared for values of x from 1 to 4. And we're going to rotate this curve fully around the x-axis to generate a three-dimensional solid, which is called a solid of revolution. So when we rotate the curve by 360 degrees around the x-axis, we're going to obtain a shape looking something like that if we're looking from the side on. But perhaps a more useful view for visualizing it is to look at it from a slightly different perspective, and then we can see the solid rather more clearly. Now what we really want to try and do is work out what the volume of this resulting solid is. So, we're attempting to evaluate the volume of a solid of revolution generated when we've got the curve y equals f of x between x equals a and x equals b is rotated fully about the x-axis. So there's my little bit of the curve, and there's the resulting solid of revolution. Now what we need to do at this stage is we need to consider a small strip underneath the original curve. And this small strip is going to start at x and have a width of delta x, and it's going to have a height of f of x. Now when we rotate this small strip completely around the x-axis, what we're going to do is we'll obtain a very, very small cylinder. And this cylinder is going to have a radius of f of x and a height, or depth be a better description in this case, of delta x. Which means that it's going to have a volume of pi times the radius squared times h, so pi times by f of x squared times by delta x. Now, we can estimate the volume, v of x, of the solid of revolution by adding up the volumes of all of these disks as x varies from a to b. So we can say that v of x is approximately the sum between x equals a and x equals b of the volumes of these disks, and the volumes of these disks are pi times f of x squared times delta x. Now, to improve the estimate, we need to make delta x smaller. In other words, we need to use many more thinner disks. And if we want to turn it into an equals sign, we're going to say that v of x is the limit as delta x tends to 0 of the sum between x equals a and b of the pi times by the f of x squareds delta x's. But in the previous video we saw that we can replace a limit of a sum like this by an integral. So we can actually say that v of x is actually the integral between a and b of pi times f of x squared. Of course, we've got the equation of the curve was y equals f of x, so we could say that v of x is equal to the integral between a and b of pi y squared integrated with respect to x. Now this means then now that we can calculate the volume of the solid obtained when our original curve y equals 1 plus 0.1 x squared between x equals 1 and x equals 4 is rotated fully about the x-axis. We know that v of x is the integral of pi y squared dx. The pi is a constant, so we can pull the pi right outside the integral sign. So we've got pi times by the integral of y squared dx, which gives me pi times the integral between 1 and 4 of 1 plus 0.1 x squared, all squared. So we need to expand our brackets first of all. So that's pi times the integral between 1 and 4 of 1 plus 0.2 x squared plus 0.01 x to the power 4. The integration then is nice and easy. So we've got pi times by x plus 1/15 of x cubed plus 1/500th of x to the 5. And we need the values of that when x equals 4, take away the value of that when x equals 1, and then multiply the whole lot by pi. When we put x equals 4 into the expression x plus 1/15 x cubed plus 1/500th x to the 5, we obtain a rather nasty fraction, namely 3868 over 375. And when we put x equals 1 into the expression x plus 1/15 x cubed plus 1/500th x to the 5, we obtain the fraction 1603 over 1500. And so the volume of revolution then is going to be pi times by 3868 over 375 minus 1603 divided by 1500, which gives me 4623 divided by 500 pi, or approximately 29.05 units cubed. So we now know what the volume of the solid obtained when the curve y equals 1 plus 0.1 x squared between x equals 1 and x equals 4 is rotated fully about the x-axis. But what happens if instead of rotating about the x-axis, we rotate about the y-axis? Well, the resulting solid is shown in green in the second diagram on this screen. Completely different shape from the previous one. How are we going to evaluate its volume? Well, we're going to do very much the same thing, except this time, instead of taking strips parallel to the y-axis, as we did in the previous case, we're going to take strips parallel to the x-axis. So, to evaluate this volume, we need to start by considering a small strip which is perpendicular to the y-axis, starts from a point between C and D on the y-axis, and goes out to meet the curve. The width of this strip will be denoted by the x value of the point where the strip meets the curve, and the height of this strip we'll denote by delta y. When this strip is rotated fully about the y-axis, we're going to obtain a small cylinder whose radius is going to be x and whose height is going to be delta y. So the volume of that little cylinder is going to be pi times by x squared times by delta y. To obtain an estimate of the volume Vy of the solid of revolution, we need to add up the volumes of all of these little disks, as y varies from C to D. So we can say that Vy is approximately the sum between y equals c and y equals d of pi times by x squared delta y, because the volume of each little cylinder is pi x squared delta y. To improve the accuracy of this estimate, we must use many more much thinner disks. And to replace the approximately by an equal sign, what we really need to do is take the limit as delta y tends to 0. So we can say that Vy is going to be the limit as delta y tends to 0 of the sum between y equals c and d of pi x squared delta y. Now we saw previously that we can replace this idea of a limit of a sum by an integral. So we could say that Vy is the integral between c and d of pi x squared integrated with respect to y. Now there's a couple of important things to note about this formula. First thing is, notice that the limits of the integral are now y limits. Y varies between c and d. And then secondly, notice that to do the integration we will need to be able to write x squared in terms of y. So let's see this in practice and calculate the volume of the solid obtained when the curve y equals 1 plus 0.1 x squared for values of x between 1 and 4 is rotated fully about the y-axis. Well, we've got Vy is the integral of pi x squared dy. We're quite entitled to pull the pi outside the integral sign, so we can write it as pi times the integral of x squared dy. We need to think about the limits. Now, when x is 1, the value of y is 1.1, and when x is 4, the value of y is 2.6, and since y is an increasing function of x, we know that that means that y varies from 1.1 to 2.6 without going outside those values. So the limits then are 1.1 and 2.6. But we also, before we can do the integration, have got to express x squared in terms of y. The fact that we know that y equals 1 plus 0.1 x squared means that we've got y minus 1 is 0.1 x squared. Multiply each side by 10 gives me 10 times y minus 1 equals x squared. So I know that x squared is equal to 10 times y minus 1. So I've the volume of revolution that I've got when the curve is rotated fully about the y-axis is given by pi times by the integral between 1.1 and 2.6 of 10 times y minus 1, which is pi times by the integral of 10y minus 10. So what I've got is the pi times by the value of 5y squared minus 10y when y equals 2.6 minus the value of 5y squared minus 10y when y is 1.1, which gives me pi times 7.8 minus 4.95, or in other words 12.75 pi, or an approximate value of 40.06 units cubed. So we now know how to work out the volume of revolution when a curve y equals fx is rotated fully about either the x-axis or the y-axis.